Question 5 from the 2019 Advanced Higher Physics exam from the SQA. Juno is a spacecraft with a mission to survey Jupiter. Juno is in an elliptical orbit around Jupiter as shown in figure 5a. Remember, an elliptical orbit is much like an egg-shaped orbit. Now part A asks us, the gravitational potential at point A in the orbit of Juno is minus 1.70 times 10 to the power 9 joules per kilogram. And for 1 mark, we are asked to state what is meant by gravitational potential of minus 1.70 times 10 to the power 9 joules per kilogram. Well, our definition is as follows. This is the value of the work done by an external force in moving a unit mass, that's where the per kilogram comes in, or just 1 kilogram, from infinity to that point in space. Now, if we think of a diagram of Jupiter and the surrounding gravitational field, we can draw that gravitational field or think of it in terms of a well, only we call it a gravitational well. And you can see it out here at infinity from the planet. We take the gravitational potential to be 0. And we come closer to the planet, we see that the gravitational potential becomes more negative. Because when we move a mass, do work on the mass, moving it towards the planet, we are actually going in the direction of the field, the gravitational field. And that means that the external force is doing negative work. Now that may be a bit hard to get your head around. Another way to think about it is this. At that position, if you've got a unit mass at that position, you have to supply plus 1.70 times 10 to the power 9 joules per kilogram of work to get that unit mass out to infinity away from the planet. Or think of it this other way. That's the amount of energy, the plus 1.70 times 10 to the power 9 joules per kilogram to take that mass away out of the well and away to infinity. So some people get a wee bit mixed up with that minus sign, but that comes out in the integration, in the integration of the work done. Remember, work done is force times distance. So in this case, the gravitational force is actually pointing towards the planet. So if you move something towards the planet, you'll end up doing negative work on it. And that negative work merely means then simply this. If you can look at the reverse side of that, it means that's the amount of energy in plus value that you need to supply to that mass to take it out of Jupiter's gravitational hold, its gravitational world, and put it to a point in infinity where the gravitational potential is 0. Question 5, part B. At point B, Juno is 1.69 times 10 to the power 8 metres from the centre of Jupiter. And we have to calculate for 3 marks the gravitational potential at point B. So our data sheet gives us this here. And you can see it's the top equation where V is equal to minus Gm over R. That's the equation we're going to use. That's the gravitational potential equation. Minus G capital M over R. So we write that equation down then. We can put down the potential at this point B, we'll just give it subscript B, is going to equal to minus G times M over R. And now it's time to fill in the numbers, and we can do that by looking at our data list, our data sheet list like that. You can see capital G, which is going to be the universal constant of gravitation, is 6.67 times 10 to the minus 11. So we're going to have VB is going to equal to minus, put this in a bracket, and 6.67 for capital G times 10 to the minus 11 multiplied by the mass of Jupiter. And on the data sheet there you can see the mass of Jupiter is 1.90 times 10 to the power 27 kilograms. So we'll mark that down then. Mass of Jupiter 1.90 times 10 to the power of 27 kilograms. We'll put that in a bracket. And then we've got to divide by the distance R, which is the distance from the centre of Jupiter to that point B, and we're told it is 1.69 times 10 to the power 8. So we've got 1.69 times 10 to to the power 8. I'm just leaving the units out there now, but we do know what the units for potential is going to be joules per kilogram. We're going to get a minus answer, and when we do the calculation, we get 7.50 times 10 to the power 8, and it's going to be joules per kilogram. Remember, potential is defined as the work done in bringing a object of unit mass, or 1 kilogram, from a point infinity to that point in space. So that's why we must have per kilogram involved. So that's your answer for 3 marks. Question 5 continued, part C. The mass of Juno is 1.6 times 10 to the power 3 kilograms, and for 4 marks we're asked to determine the change in gravitational potential energy of Juno when it is moved from point A to point B. Well, a quick glance at our equation sheet, and we can see the equation we're going to use is the middle one there, EP, representing the gravitational potential energy, and that equals V, which stands for the gravitational potential, times the mass. Now we can modify that in terms of deltas to mean change in. So we can say that the change in the potential energy is equal to the change in the potential multiplied by the mass. That's all we have to do. So our first step is to work out the change in potential between position A and position B. And we know that at position A, the potential is minus 1.70 times 10 to the power 9 joules per kilogram. And we know at position B, the potential is minus 7.50 times 10 to the power 8 joules per kilogram. So all we have to do is work out delta V, and we can say that delta V, the change in potential, is equal to the potential at B, VB, take away the potential at A, VA. And be very careful, because the potential at B and A are both negative. So we start off with the negative 7.50 times 10 to the power 8 joules per kilogram. That's the potential at point B. Take away and put a bracket on it. Minus 1.70 times 10 to the power 9 joules per kilogram. Close your bracket. And if you do that properly in your calculator, you're going to end up with a positive number of 9.5 times 10 to the power 8 joules per kilogram. And that's us got our change in potential. So to find the change in potential energy is straightforward enough. Delta EP is just simply going to be equal to delta V multiplied by the mass. So it's going to be equal to 9.5 times 10 to the power 8 joules per kilogram, and multiply it by the mass of Juno, which is times 1.6 times 10 to the power 3 kilograms. You can see the 2 kilograms cancel out, and you're left with a value of the change in potential energy to be the value of about 1.52 times 10 to the power 12 joules, and that's the change in potential energy.